AP Calculus, Unit 1, Lesson 1. In this lesson, we're going to learn how to calculate the average rate of change from data points or from a graph, and to estimate instantaneous rate of change at a point. The key formula that you'll need for this lesson is to find the average rate of change, which is the change in position over change in time, or delta S over delta T. You will also see delta S in your book referred to as displacement or net displacement, so don't worry if you see that. It just means a change in position. So let's calculate a rate of change from a table. So we have a table on the left, and we want to calculate the average rate of change from time 1 to time 4. So we're simply just going to look at the table, find the distance at time 4, which is 30, the distance at time 1, which is 12, and subtract them over 4 minus 1, which is the change in time, and calculate that and get an average velocity of 6 feet per second. We also want to calculate average rate of change from a graph. Here we have a graph, and we want to find the average rate of change from time 1 to time 4. I've drawn in the secant line to show that average rate of change. And this is the same as the table. Once you have the 2 points, you just take the y coordinates and subtract them, and take the x coordinates and subtract them, and divide, and you find the average velocity. So in this case, the average velocity was 0.5 feet per second. In order to estimate instantaneous rate of change, you either have to select a point on either side of the point of interest, select a point equidistant on both sides of the point of interest, and once you've done that, then you'll calculate the average rate of change. Now let's look at an example of that. Here we have a graph of a parabola, y equals 1/4 times the quantity x minus 1 squared plus 2. The secant line is a solid line. The dashed line is the tangent line, which represents the instantaneous rate of change. And so we will try 3 methods to do this. We can grab a point and drag it close to the point of interest and get an estimate. And here we're on the right-hand side. We could also take and drag that point to the left-hand side and get an estimate of the instantaneous velocity. Or the third way is we can take a point equidistant on both sides and use that to develop the estimate of the instantaneous velocity. Either way are fine for estimating. So here is the equation we just saw. Y equals 1/4 x minus 1 squared plus 2 at x equals 3. Here we're picking a point on the right and the point of interest at x equals 3 and calculating the instantaneous rate of change. And we get 1.25 for that approach. If we look at example 2 and we choose a point on the left side of the point of interest, then we're going to have f of 3 minus f of 2 over 3 minus 2, which gets us 0.75, slightly different. The third method is to pick a point that is equidistant on both sides. So I pick the point 4 and 2, which is in the middle, or 3 is in the middle of that. So we get 4.25 minus 2.25 over 2, which gives us an estimated rate of change of 1. So what have we learned in this lesson? We saw that the average rate of change is the slope of the secant line. We also saw how to calculate the average rate of change from a table or a graph by the formula on the screen. Delta f over delta x equals f of x1 minus f of x naught over x1 minus x naught. We also saw that instantaneous rate of change is the slope of the tangent line at x naught, and that the instantaneous rate of change is the limit of the average rate of change. In other words, if we got that second point closer and closer to x naught, we would get a better and better estimate. However, we couldn't put the second point on x naught because then we would have a dividing by zero situation. Of the top and the bottom would be 0 over 0.